Well, I think we'll get started. So welcome to the compilation session of ICFP. We have two talks. If you are watching from YouTube, don't forget that you can ask questions on Discord. There are channels for each of the threads, for each of the talk. You can look at them. The threads are not in order, so just search the ICFP channel for compilation and you will find them. So our first speaker is Patrick Bahr. Take it away.
All right, thank you. With Graham Hutton. And so what we're doing in this paper is showing how to calculate correct by construction compilers for concurrent languages. Right? So, and I should start out by explaining what exactly I mean by calculating a compiler. So this is the setting we have, right? We have given the syntax and semantics of a programming language. The syntax is given by an algebraic data type like this, here for a very simple expression language. And the semantics is given by an interpreter for the language, which in this case is simply evaluating this simple expression language, right? And so what we want to get out of this situation is a compiler, right? And not only that, we want to get to this compiler by some kind of mechanical process, right? And not only the compiler itself, we would also want to have some kind of assurance that the compiler is actually correct. So out of this process, we also want to have a proof of the compiler specification, right? That says something like this, right? So if we compile the expression E into code, and then if we run that code on a virtual machine, then the result should be the same as if we just evaluate the expression outright. So that's where we want to get. So how does calculation get us to that situation? Well, the approach is to simply start by proving this compiler spec over here, right? We just try to prove the compiler spec even before we have the compiler itself. And then as we do the calculation using equational reasoning, the definition of the compiler will fall out of that. And that might seem magical, but I'll show you in a bit how this works. So stay tuned. And what we did last year at ICFP is show that this also extends to monadic semantics. So where the semantics of our programming language is given in terms of a monad that is able to capture also non-determinism and non-termination, right? And in order to do this, also our spec now has to replace equality for a bisimulation relation down here, right? So, but the whole machinery still works as before. And so now the goal of this talk is to find a monad that allows us to express concurrency, so that we can actually define the semantics of a concurrent language in this fashion, and then get a compiler out of this by calculation. So we also need some form of nice algebraic properties that allow us this kind of compositional reasoning. So that's the goal for this presentation. So to get more into detail about what we need, right? So these two things. The first thing is we need a monad to express concurrency. So what do I mean by that? So we need some kind of parallel composition operator, right? Something that takes two computations and composes them in a parallel fashion. We need some kind of observable effects so that we can actually observe that something happens concurrently, and we need some form of communication so that parallel threads can communicate with each other. So that's in terms of expressivity. And then secondly, we need nice reasoning principles for our calculation approach, right? So nice comprehensive algebraic properties that allow this. And so what we do in this paper is to construct such a monad, right? And this is based on recent work on choice trees. And we add two things to choice trees. First of all, we do a very small refinement of the syntax and the semantics of choice trees, which gives us slightly better algebraic properties, but which we need actually for our calculations. So these turned out to be crucial in the end. And secondly, we add a codensity construction on top of this, which we need for expressivity. So actually to be able to express the semantics that we want for our concurrent language. And then secondly, we actually apply this monad to a language, higher order concurrent language, namely essentially a lambda calculus plus a fork forking of parallel computations, and then channel-based communications between channels. And so we formulate the semantics for a language like this, and then use this machinery to get a compiler out of this using calculation techniques. So in this talk, I will mainly focus on the first part here. How do we get to this monad? And then I talk a bit about the second part, but not sort of in detail of how we do this for this particular language. All right, let's get into this. So as I said, this is based on this recent work on choice trees presented at Popple this year. And so this is the definition of choice trees. Very sort of compact definition. And so choice trees allow us to model computations with non-determinism, right? And so a choice tree has these two arguments, and the A argument over there, this tells us what the return type of this computation is. So whenever the computation terminates, it will give us a value of type A. And we have pure computations in this now constructor that expresses these. And then the second argument defines what kind of algebraic effects we can use in our choice tree monad. And then apart from this, we also have non-determinism, right, in the form of non-deterministic choice operator, the plus here, and then also its unit, the 0. And then finally, we can also express non-terminating computations in the form of this later constructor. And this works very similar to the delay monad, if you're familiar with that. All right, so that's the definition of choice trees. And it's very expressive. So it forms a monad. We can also express parallel composition operators for this structure. Right, and here I just mentioned one of these parallel composition operators, this right-biased parallel composition, which takes two computations, this one and this one, but it only returns the result of the second one. It just throws away the result of the first computation. It only executes it for its effect. And so this will be sufficient for our purposes here. All right, so this was the syntax of choice trees. Now to the semantics of choice trees. We can give semantics by simply giving a label transition system for these. It's fairly straightforward. These are all the rules that we need for that. And once we have that, we can define our bisimilarity relation in the standard way that most of you will know. But the upshot of this is that this bisimilarity relation has very nice algebraic properties, right? So exactly the ones that we need for our compiler calculation, right? We have monad laws. We have that the non-deterministic choice forms an idempotent commutative monoid. We have nice algebraic properties for parallel composition. So this works very nicely. So this is all set for our purposes. So let's use this for a very simple example language, just to show you how this works. Right, and so this is a very simple concurrent language, which just extends the simple arithmetic language that I showed you in the beginning with a print primitive that prints an integer to, say, the screen, and then also a fork primitive that forks off a computation that evaluates this expression, right? And down here, you have given the semantics of the language in terms of these choice trees, right? And here we have the effect, so it can use the effect of printing to the screen. And then the semantics for val and add are straightforward, right? For the val, it just returns the value, and for addition, it just evaluates x and y and adds their result. And then here at the bottom, we have that the print statement simply evaluates the expression x and then prints the resulting integer. And then interestingly here, then the fork, where the actual parallelism happens. So what happens here is the fork just returns 0, right? But in parallel, it evaluates the expression x. Right? So this is our semantics, very compactly defined using choice trees. But then the question is this actually is it the right semantics, right? And as it turns out, it's not. So if we look closer and check a very simple example here, the add fork x, y, and see how this works, right? And sort of compare with what we would expect the semantics of this to be. Right? So if we unfold the definitions of the semantics, right? We have the semantics here of the fork down here, and then the remainder is here the semantics of add. And then we can apply our algebraic reasoning principles to simplify this, and it turns out that the semantics of this expression is actually this here. And so this is the bind, the monadic bind operator. So what it actually does is it first evaluates x, and then afterwards it evaluates y. So there's no actual parallelism going on. So it's kind of disappointing since we have a fork in there. So what we actually would expect is that the two are evaluated in parallel, right? But this does not happen. So clearly something is wrong with the semantics that I've shown you. So let's look at the semantics of fork a bit more closely. Right. So this does not work. There's clearly an error in there. And if you look at the literature and sort of how you model the semantics of a fork, you would see something like this, right? So to evaluate a fork in some evaluation context, what you do actually is, well, you evaluate the remainder of the evaluation context C and replace the fork with the value 0 that it returns, and then in parallel to that, you evaluate x over here, right? So this is the semantics we actually want. But in order to actually use this in our definition, so this is not actually a valid actor or Haskell, we can easily transform this into a form that uses continuation, right? So here we extend eval so that it takes an additional argument, the continuation argument, and then sort of we simulate this evaluation context style using this continuation instead. So here the continuation is used on the right-hand side of the parallel composition, and then on the left-hand side we evaluate x with the identity continuation, if you will, to the right. And so this is now the right semantics. When we check it out, we see that that's the one where we need for fork. And this works all nice and well for our semantics of the simple expression language, but if you actually want to reason about the semantics, you'll find out that we can't really use our nice monadic reasoning principles. We end up having to prove sort of ad hoc lemmas about continuations and how they interact with the eval function. So and these sort of ad hoc lemmas, they look very much like monad laws, but not quite, right? So it's a bit of a shame that we have to give up just because we have to introduce these continuations. So the fix is very easy in a way, right? So because there's a standard construction to sort of build in a continuation into your monad. It's the codensity monad construction, and that's exactly what we do, right? So we extend our choice tree monad with continuations in this fashion, right? Using the standard codensity construction. So now a codensity choice tree like this works like this. So it takes a continuation that produces a choice tree, and then we produce out of that another choice tree. So it has built in the continuation. But the upshot really of this construction is twofold. First of all, we can lift all of the operations on choice trees, right? The monadic operations, the non-deterministic choice, all of that can be lifted to this codensity choice tree construction, right? And importantly, also all of the algebraic laws follow along, and we have the same reasoning principles that we can use. So that's nice. And secondly, we also get an additional law that tells us how monadic bind interacts with parallel composition, and that shows that this is the right parallel composition for modeling how fork works. Right. So if we have two parallel computations, P and Q, and followed up with a computation F, then we can move that computation F inside the parallel composition to the right. Right, and so this will turn out to be exactly the match that we need for our fork instruction. And we get this by defining the parallel composition on codensity choice trees like this, where, okay, so this codensity choice trees, right, that they take a continuation as the first argument, which we take here as an argument, and then we pass this on to only the right-hand side of the parallel composition, right? That's where we want to continue the computation. Right, and that's what we use for modeling the semantics of our fork. So now we can revise the semantics that I've shown you earlier to now use codensity choice trees, right? That have the continuations built in, and it looks very much the same. The only difference is now that we use the codensity choice trees. And now we can check that our example from earlier has has the expected semantics now, right? So if we have adding fork x to y, we can unfold this definition, and it looks very much like the definition we had before, but now we have this additional algebraic property that tells us how parallel composition and bind interact. And so now we can move this bind here into our parallel composition like this, and now we can simply apply our standard monad laws and simplify this to this expression, right? So this is exactly what we would expect, right? So that eval x is evaluated in parallel to eval y, and so now this is the right semantics that we want for our language. All right, so now we have this in place. We have our monad. We have the reasoning principles that go with it. We have the semantics of our language. Now let's try to calculate the compiler, right? So we have given the syntax and semantics of our source language like this, and we want to derive a compiler. And as it turns out, not only do we get a compiler, we get a whole bunch of other stuff too with this methodology. So in addition, we also get the actual syntax of our target language, so the code that is produced by the compiler, along with its semantics, which is given here as this exec function that defines a virtual machine, a stack machine, that executes this code, right? So it takes a code as the first argument, and then the stack, which is simply a list of integers, and then it runs the code, and gives us how the stack looks like after we executed the code, right? And it uses the same effect structure, the code density choice trees with this print effects that we also have in our semantics of our source language over here, right? And that's exactly what we need for the reasoning, so that the semantics of the source language and the target language live in the same monad. Okay, so this is what we want to get out of this, and we also want to get out of this the proof of the compiler spec, right? So, and this looks like this now, right? So we want that if we compile the source expression and run the resulting code, starting with the stack S over here, this should be the same if we would just evaluate e to a value v and then stick this resulting value v on top of the stack, right? That should be the same. That's what we want. Now, to make the calculation go through a bit more smoothly, we generalize this property a bit. That give us a nicer induction hypothesis, where our compiler now, in addition, also takes a continuation argument. So now the compiler says, okay, give me an expression, and I produce the code for this expression, and then I follow up this code with this additional continuation code afterwards, right? So we have this additional code continuation in this compiler. So now the compiler spec is also generalized in this fashion. So it takes this additional code continuation that also shows up here on the left-hand side. So after we have put the value here on the stack, we follow it up by executing the continuation also. Right, so now this is the spec that we want to work with, and now we can crank the handle and go through the the calculation machinery. Right, we start to prove this property, and as we prove this property, we get those definitions out: the compiler, the code, and semantics. All right, let's try this out. So this is the spec again at the top here, and what we're going to do is we're just going to prove this by induction on E, the structure of the source language. And we started with a simple case, namely that E is just integer literals, just a val n case. And this is how it goes, right? So we start out on the left-hand side of our spec, and now our goal is to massage this term so that we eventually end up in the right-hand side of the equation here, right? So using the algebraic properties that we have at hand. Now, of course, the problem is we don't know quite yet what the right-hand side looks like because we don't have the definition of the compiler yet, right? So this part is missing here. What is the compiler? Well, but that's where the definition of the compiler will actually fall out of this computation, out of this calculation, because what we do now is we simply try to get into a state, into a term of this form, where our goal is to have some kind of term down here, C prime, that is of type code, and then we simply make the connection to the thing we want to prove work by fiat, by simply saying, okay, then we simply define the compiler to be exactly equal to what we have calculated, right? And now the proof will go through by definition, right? We can simply read off the definition of the compiler by reading off the last line of our calculation. So this is what I mean by the definition of the compiler will simply fall out of the calculation. All right, so let's try this out. So the very first step is just applying the definition of eval, so the semantics of our language. So we get that val n evaluates to return n. Then we can apply our monad law, so left unit law that says, okay, now we can replace n for v in here. So now we have n on top of the stack. And now there was just one step missing, right? Our goal is to get to the state down here, right? And the problem is the stack does not line up. Here we have the stack with an additional argument, with an additional element on top, which we don't have down here, right? So which means that we have essentially an equation to solve. How do we make these two things equal, right? We have to solve this equation here, essentially. And again, the strategy is to solve this by fiat, by simply make this into a definition. Right? And how do we make this into a definition? Well, we have to make sure that all the variables on the right-hand side also are bound on the left-hand side. And then this turns into a definition. Right? So S occurs on the left-hand side. That's good enough. But we also have C and N over here, which don't appear on the left-hand side. But we can make them appear there by simply sticking them into the C prime, which we can freely choose. Right? And we simply choose C prime to be, well, a new constructor, which we call push, which would be apparent why we call it push, with these two arguments n and c, right? And now if we stick that in, this is now a definition for our exec function. And now this solves the equation that we need to fill in there. And not only that, we have just discovered a new instruction for our target language, push, and also its semantics, which is given by this equation, which we have just introduced in order to fill the gap in the last step here, right? So we define this new instruction and its semantics, and that fills in the gap so we can close the proof. And not only that, now we also can read off the definition of our compiler, right? So we compile an integer literal simply to a push instruction. Okay, so this was the simple case, the val case. Let me show you also the fork case, how this works, and I run through it very quickly. Again, we have to prove this equation, and the way that we do is we start on the left-hand side, and we start by applying the definition of eval, so the semantics of fork. We have it here. We can simplify this by applying the algebraic laws that we have, we get into this state. And then our goal now is to apply the induction hypothesis, right? To apply the induction hypothesis for x here. So we must be able to turn this term here into something that matches the left-hand side of our induction hypothesis. And again, we do this by fiat, by introducing a new instruction in our code and an equation that defines its semantics so that it exactly has the right shape so that we can apply the induction hypothesis now. That's exactly what we do now. So we apply the induction hypothesis, which gives us over here, and now we're almost there. Now again, we are in a state where we have to solve an equation, so we get up to the final state here, our target, and again we solve it by fiat, by introducing a new instruction along with an equation that defines its semantics, and we're done, right? So now we have discovered a new instruction, this fork instruction, along with its semantics, and we can now read off the definition of the compiler for the fork expression in our source language. So that's how this works, and we can do this also for the rest of the source language. And so this is the compiler we get out. It's fairly simple. And we also get out the semantics of our target language, right? Which is the stack machine, and it's a tail recursive function with parallelism in there. And so now we have calculated a compiler for our very simple concurrent language. All right, that brings me to my final slide. So there's more in the paper. So if you're interested in sort of the details of the differences between the choice trees, how we use them, and how they were originally introduced, so that we get better algebraic properties, that is also in the paper. The differences are subtle, but they're very crucial for our calculations. You also find the details of the compiler calculation for this concurrent lambda calculus. right, which features a fork instruction and channel-based communication. So this is the first time we have a derivation of such a compiler for such a language. And all of this is formalized in ACTA, so including the definition of choice trees, all the algebraic properties, but also the compiler calculations themselves. So if you're interested, please check those out as well. And that's all I had. Thank you.
Please, if you ask a question, remember to introduce yourself first.
Hey, this is Adam Chapala from MIT. The interesting thing about the compilers that you were showing us with this technique is that they get to invent their own target languages. And in some sense, there's a cop-out case whenever going gets tough, you just add a new instruction that does what you want. How can this approach be applied to cases where the target language is fixed?
Sorry, the last sentence?
How can you apply this approach to situations where the target language of the compiler is dictated to you and you don't get to choose it?
Yeah, I mean, then you sort of you're more constrained, right? You're only allowed to pick from whatever instructions you have, right? In a way that reduces your search space in your calculations, right? But it also might make the problem more difficult because you might have to string together several instructions so that you can solve the equations, right? So you might have a bit more work to solve the equations that I showed you, right? But it also it constrains you a bit more. But I don't see in principle a problem with that. Yeah.
Thanks.
I expected you to solve the problem that you introduced continuations for in a slightly different way. So I looked at that and I thought, oh, choice trees are not sufficiently expressive because they cannot express computations that deliver a result and then continue to perform effects. So you could have split the now constructor into two constructors, one for delivering a result and then another for halting. Did you consider that? Does it run into problems along the way, or? So
you split the now into what?
Split the now into deliver a result with and then continue executing code, and a separate instruction to halt. So you can imagine parallel computations that can deliver a result, but then continue to perform effects afterwards. And that change, I think, would have meant that you didn't need to introduce continuations.
All right, so you basically built them into the. I didn't catch all the details. There's a lot of echo in the room. So the idea is to build it into the definition of choice trees themselves, so that you can have some continuation that you want to perform after you've halted, essentially.
Yes, exactly. Or some action that you want to continue performing after delivering your result.
Right. I suppose that could work. I haven't really thought about this. Yeah.
Thanks.
Hi. Working? No.
You're good. It works.
Okay. Zhishen Yang from Imperial College London. So in your choice trees, you first define a transition system on your choice trees, and then obtaining a bisimulation from the transition system. How does this compare to just define an algebraic theory on the operations, so you directly get a equivalence relation from the algebraic equations? Is it more general or more flexible?
Right. So the proposal is to start with your algebraic theory, right?
Right.
So that it sort of fits with what you need. I suppose you could do that as well, but then you still have to sort of prove that it is consistent, right?
Yeah, sure.
And sort of here we sort of take a different route. Yeah, that could be a possible approach to that.
Okay. Thank
sort
you.
of that you carve out exactly the kind of laws that you need for your proofs. Yeah. All right.